Let's take a look at what is involved in the minimization of the total potential energy of the beam. The total potential energy of the beam is equal to the work done by the internal forces minus the work done by the external forces. Okay, so the internal forces contribute to the potential energy and the external forces also do, and they have opposite sign. Let's take a look at the work done by the external forces first, because that's a little bit easier. So the work done by the external forces can be written this way, and let me explain that. P here would be the load that you apply at the end of your cantilever beam, and that load is going to move a distance equal to that. That's just going to be the value of this at the end of the beam. So that's just the length of the beam. Okay, so if you write P versus the distance, okay, when you apply the load, initially there is, there's no displacement, and then it's going to build up, and then it's going to go to the value shown over here, and the area under that curve gives you the energy. And that's what's given over here. Next, let's take a look at the contribution of the internal forces to the potential energy. This is more subtle, and it looks like that, and I had to explain it to myself, so I'll let me indicate how, what this expression involves. Okay, so if your beam, your deformed beam looks something like that, and the cross section over here is like that, and that has to be 90 degrees, and that's part of the assumption in the Euler-Bundel beam theory, as we have looked at. And so we want to know what is the work done by the internal forces. And if I take an infinitesimal or vanishingly small chunk anywhere in the beam, okay, and I blow it up, so it looks like that. And let me say that's the x direction. So we have the internal force is only, the force in the x direction. It could be pulling that infinitesimal chunk, or it could be pushing it, and that's equal to sigma x times dy dz, where dy would be that length and dz would be that length. Okay, so that's where you get that from. And then if I do the same business of force versus displacement, okay, now the force is, given over here. So let me say this is the force versus the displacement on this infinitesimal chunk. There's a contrast to the external force, because the internal force, is going to be 0, and then as I apply this this external load, it's going to keep increasing until it reaches the final deformed state. And since we're assuming that the stress is directly proportional to the strain, it's going to be a straight line. So that's going to be given by that, and this is going to be epsilon x times dx. You can convince yourself of that. And the final one, actually this distance over here. And this area will give me the work done by the internal forces, and so you get the term in the integrand, and because you have this buildup of the internal force, that's why you get the half here and not half over there. And it took me some time to kind of figure out why that half is over there. So hopefully that's a convincing explanation. And then you have to you have to add it up over all these infinitesimal chunk, and that's where that integral over the entire volume of the beam comes in. And then you can be, as we've seen, we can write the strain, the stresses and the strains in terms of this this function over here, and that's what I've done there. I won't go through the math, but in the process, if you work out the details, you will get the the Young's modulus, which is a material property that comes from going from the strains to the stresses, but you'll also get a cross-sectional property, the moment of inertia. So it depends not only on what this function is, but it also depends on the cross-sectional property and the Young's modulus. And so in ANSYS, we have to give, these two parameters as well as the length of the beam. So we need to find, so the problem now is we need to find this function such that this is minimized, that an integral is minimized. Finding a function to minimize an integral is not an easy problem, but ANSYS will solve that approximately for us using the finite element method. Let's take a look at how it's going to do that.